collaboration with my colleagues at Intel Labs, Todd Anderson, Lindsey Kuper, Ehsan Totoni, and Tatiana Shpeisman, and also young Vitek from Northeastern. So in the scientific computing community, people love to use languages like MATLAB, Python, or R because they're great for productivity reasons. They use it to write prototypes and experiment with their implementation. And these languages are great because they're safe. There's bounce checking for array accessing, and also the memory is automatically managed through a garbage collection. And also these languages are typically dynamically typed. They're more forgiving and easier to work with. And there is usually a good support in the dev tools. They usually provide an interactive debug session and repo loops for you to quickly see the results before you complete the whole program. And they have a growing ecosystem with lots of libraries, and the community the community by and large is growing more than the traditional HPC community. So that's all great, but what about performance? Option one is when you have a prototype ready, now you want to run it with a bigger data set, and you find out the performance may be not up to your expectation. So what do? The option one is just re-implement the same algorithm in a traditional HPC language like Fortran or C or C++. You can get pretty fast, but that all usually comes at a cost. So it really depends on what you mean by fast. The implementation can greatly differ. With very good implementation, you can get there, but if you're not careful enough, you may still get suboptimal performance. And there are all sorts of drawbacks with this kind of approach. Because it's low level, you have to care about a lot of details about hardware, and your program will be hard to debug, and they're not safe. It's hard to maintain as the hardware evolves. You have to rewrite part of your program to get back the performance. And just in general, it demands a skill set that's not possessed by a lot of domain scientists. So another approach is just let the experts write these high-performance routines as a library, and we use that. And most of existing productivity languages, they took this approach. They have bindings to low-level libraries such as OpenBLAS and MKL. They have a good performance for each function call, and because the API is well specified, they're fairly easy to use. However, the API comes as both a good way to discipline your program and also as a barrier. You cannot go beyond what the API provides. So when you make a function call one by one, they're usually not cache friendly. If, let's say, you're traversing a big array, doing some operation with one function call, then traversing the same array with another function call, the traversal cannot be reused. And also, for this reason, library calls, although each individual implementation can be parallelized, implemented in parallel, but when you make calls one after another, these calls do not compose in parallel. So what people often do is to take a third approach. They use a domain-specific language and its optimizing compiler. So in this restricted domain, you can usually provide a higher level of abstraction to write your program, and they come with domain semantics. You don't have to concern about low-level details, and yet such semantics helps the compiler to better optimize your program, and you can get very good performance. But with domain-specific languages, they usually come with a steep learning curve. And also because it's their own language, it's not the popular language or general purpose language you use, they're usually hard to debug. The support for the tool chain is limited, and the user community is just not there. And also the libraries and all that may not be on par with the popular languages. So to solve this problem, we propose that we use something that we call a non-invasive DSL. So it provides an interface just like a library. You can use it just like ordinary library, and when you run it, you can either take the library approach to invoke it like a library call and debug it just like what you do usually. But if you would like some performance, you can flip a switch, and then all the parts that you write using this DSL will be compiled by a compiler. So you get advantages of both the library approach and the DSL approach. So before we go deeper on this, let me just give you some context. We implement this system in a language called Julia. It's a young language. It's dynamic language, just like Python or R. It has a syntax that's similar to MATLAB, very, very similar to MATLAB. So you can basically port your MATLAB program to Julia with little modification. There are two interesting aspects of Julia. One is that it has a powerful macro system that inherits from Lisp. And also it has a type system, which is not so common in the dynamic language like Python or R. So this type system of Julia is somewhat in between a dynamic language and a static typed language. So these types, you can omit them. They're optional. But if you specify them, the language will check them as an invariant. So what happens at runtime is that before you make a function call, the Julia compiler will try to see what kind of values you're trying to pass to this function and what are the types, and you will run a type inference pass on the function you're going to call. And if all the types check out and the function itself can be converted to a lower level implementation in LVM without all the burdens in a dynamically typed language. So in that sense, it can get very fast sequential implementation, and they did. So it's implemented via LVM JIT, and the sequential performance usually is comparable to that of a commercial product like MATLAB. It's much faster than Python. So here I give an example of k-means function written in Julia. I won't go into the algorithmic details, but I will just try to walk through the features of Julia. So there are operators like minus or the power operator. These are overloaded for both scalar values and also array values. And also there are things like this dot equal. It's an operator that operates on arrays. It tries to check each element whether it's equal to a scalar value. And if it is, it returns a true in a result array or false in the result array. So it gives a Boolean array as a result. And there are library calls like a random value or just take a sum of your array or the minimum index, find the minimum index in an array. So these are library calls. And also there are array selection. You can select a range of the array as a subarray. For example, this syntax, this colon means everything in this dimension and at I index in the second dimension. And also you can select array based on another array. So this dot equal, like I mentioned, it produces a Boolean array as a result. You can select the values along this second dimension for those that are true in this Boolean array. And there's also a syntax called comprehension, which is similar to what's provided in Python, except that it's array comprehension instead of list. So you can produce, each of the comprehension produce a new array as a result. You can easily write it for a multi-dimensional array like this. And so this is our program. It implements a k-means function with relatively few lines of code, very concise. And Julia will run this with type inference. So you will try to see what are the types you pass as argument, and you will try to infer the types of the variables that's defined in this function. And if all the types can be known, you will give a very fast LVM implementation for this. And if you want to go beyond sequential performance, here's our compiler comes in. To use it, you just use our compiler. It's called ParallelAccelerator, and you just put a macro at ACC in front of the function you write. So that's it. That's the only thing you have to do. And with that, you can expect some nice performance by automatic parallelization. So this is k-means with Julia measured in running time in seconds. And even with just one thread, because we do very aggressive optimizations for this numerical computations, even with one thread, we already get like 4 times speed up. And with 4 threads, you get another 3 times, and 8 threads, maybe another 1.5 times. So with just a simple flip of switch, you can get good performance. So ParallelAccelerator, we call it a non-invasive DSL compiler for multi-core. It's written in Julia itself. You can use it just like what I showed just now, import it as a Julia library. And you will optimize a subset of the Julia language, and as well as the subset of the library calls. So for those that supported by ParallelAccelerator, we'll compile the operations to C++ with OpenMP, or there's another backend, we can compile it to LVM with Julia threads. Julia threads is relatively a new thing. So what's actually being optimized by ParallelAccelerator? There are array operators that operate on the whole array. They can be parallelized. They have inherent parallel semantics. And also reduction and all that, we parallelize those. And we support Julia array comprehension. And also we provide some other features that's not already in the Julia ecosystem, something like stencil support. We provide a construct called a run stencil. It's actually a library call. You can just run it with ordinary Julia, and we have a library implementation for this. But if you put at ACC, we will intercept this call and convert it by the compiler optimizations. And also we support parallel for loops with a add par macro. So here is our compilation pipeline. We take Julia source code. So this is done by Julia. Julia takes the source code and do some parsing and type inference and get typed Julia AST. And here is where our implementation comes in through the macro. We take the AST and convert it to domain operators like map and reduce and stencil and all that. And then we convert it to parallel construct internally that we call par4. And then with that, we convert it to a C++ code with OpenMP and SIMD vectorization pragma and all that. And eventually we invoke external C compiler to compile it to executable and then load it back into the Julia runtime as a dynamic library. Here is a brief walkthrough of the compilation process. I take one line from the k-means example. And we can see that here's array selection and here is array operator minus. It's converted. There's 2 selections. They are converted internally to select operator. And the minus between arrays becomes the map over the minus on the scalar value. And there's a power of 2, and it's converted to another map, takes the power of 2 over a scalar operation. And there's sum is converted into reduce. And the square is just operating on a scalar, so that's left unchanged. And there's this comprehension for two-dimensional array is converted into a operator that we call Cartesian array. Basically, it's like a map, but with indices, with explicit indices that you can compute for the result array, result value at that index in the output array. So this is the domain IR kind of representation we have. And next step is to convert it into parallel IR, and we lower this map operation and select operation into a parallel for loop that we call par4. So this indexing and the loop becomes explicit. And this map outside of that is fused together with the first map, and you just compute the power of 2 based on the previous computed value. And this reduction is further on is also fused into this par4 loop. Then you have a reduction variable that's S, and it gets accumulated in a par4 loop. And finally, you take the square root, and then the outer Cartesian array becomes another level of par4 that's two-dimensional, and you get to allocate the output array first, then you do the par4. So this is something we call parallel IR in our compiler. And with that is easy map onto OpenMP in C++. And we call this kind of approach switch-on performance, because you basically have the same program you would have written in Julia without learning another domain-specific language. But you can make use of our compiler by fixing this with @acc macro, or you can run it sequentially without this macro. So when you want to debug your program, you can just run it sequentially. When you want to get performance, you just flip the switch. And the set of optimizations we do. There's a lot more details in the paper, but we generally do array size inference to see whether two arrays are equivalent in size or equivalent in size in one of dimension or both of dimensions, things like that. And we do loop fusion and allocation hosting. Basically, if the allocation inside the loop, we try to see if that's redundant. Then we can pull it out outside of the loop. And we do SIMD vectorization through the external compiler, whether it's a C++ compiler or LLVM. But we do alias analysis to help with that. And here's overall evaluation across a set of benchmarks. So the x-axis is all the benchmarks, and with different implementations. We have MATLAB running on one thread, and MATLAB running on the default MATLAB running on all the threads. That's 36 threads in the test environment we have. And we have Julia implementation, Julia 0.5. That's the that's the official release right now. And it's one thread, and our ParallelAccelerator with one thread and with all the threads. And the y-axis is the relative speed as compared to Julia one threads, and it's in log scale. So the benchmarks there, most of them, they are data parallel. And some of them, they're more complex than the other, and there are several stencil workloads as well. Usually for stencils, we do pretty well, like Gaussian blur. We get like something like 600 times speed up. And for some of them, we have all the implementation, but for optical flow and Nango, we do not have MATLAB implementation, so we can compare there. But overall, the geometric mean for this is if we take the Julia implementation as 1, then with one thread's ParallelAccelerator, you get like 6 times speed up. With 36 threads, you get 36 times speed up. This 36 is just coincidental. It has nothing to do with the number of threads. It's just that we try to maximize what the hardware capability we have, but we end up with this number for all the benchmarks we have. The takeaway for this is a non-invasive DSL for parallel computing is easy to use, just like library, and it can be heavily optimized like a DSL with the facilities provided by Julia. and we can get reasonably good performance on multi-core. In the paper, we also compare with the expertly tuned Ninja performance written in C++. You can see there's still some kind of performance gap between our implementation and expert implementation. But you can get our speedups just basically for free. So that's always good. But flexibility in taking this approach is both a blessing and a curse. The blessing is that it's just as easy to use as a library. The curse is that it's unlike a restricted DSL. You cannot restrict what's coming into the program. So if the user is not careful, he can put something in that prevents some optimization from happening, and the user wouldn't know it. So we still have some work to do in performance tuning for the users, to let the user know where the performance comes from and where the performance is lacking. So maybe provide some hints to the user that if you do this kind of stuff, put a little annotation here or remove something from there, you can get better performance, something like that. But that's still part of future work. So lastly, the major enabler for this work is Julia's macro system that led us to manipulate the ST from within Julia itself. And also the type inference in Julia helps us to generate fast code without all the burdens of a traditional dynamic language. Thank you. And this is our, you can download this work from this GitHub URL.
Hi, that was very interesting. So I have two quick questions. So one is when you run in the library mode, everything is sequential, right?
Yes, that's right.
Okay. The other one is, so I actually don't know Julia, but is there a potential for side effects, when you do your transformation for parallelization, or you're just conservatively choosing only, patterns in the program to parallelize that will guarantee that there will be no side effects between the different parallel computations?
That's a good question. So the question is about side effects, how we handle those. For most of the array operations, usually usually it's written as an operator or as a function call, right? So for that, we know it's pretty safe because we know the exact semantics of that operation. We can convert it to parallel loops without any side effect in it, or the only side effect may be the assigning to the output array. So for some other operations, like when you do a comprehension, you get to grab the indices, array indices, right? So you can potentially have unsafe kind of side effect, or you assign to an environment variable, that kind of stuff. So we allow this. The consequence is that you may not get the deterministic behavior if you do that. So the user has to be aware that certain things they do, they are not safe in the parallel context.
Okay,
Does that
thank you.
answer the question? Yeah.
It's potentially, for people that don't know much about parallelization and they just use a macro, that can be potentially dangerous. But I'm sure there are some ways to finesse it.
Yeah, for the safe subset, we convert to safe implementation, but for the unsafe subset, it's unsafe implementation.
Thank you.
So do you have any support for programmers to see how those optimizations are actually taking place? So I think in your system, there are a lot of optimization like fusion, parallelization, and so maybe programmers expect those are fused, but the compiler might not do for some reason. So in such a situation, then I think there should be some support for that.
Yeah, that's a very good suggestion. Like I mentioned, we currently did not do a good job on that, but we hope to improve on that.
My question is somewhat related to the previous one. So this is sort of about user interface and feedback to the user. So for a non-invasive DSL, what kind of feedback do you imagine giving to the user about whether or not they've stayed within the performance subset, stayed within the DSL, as it were, as opposed to the Julia at large? Should it be a linter, or some kind of feedback or warnings that you're using a construct that's not well supported?
I think right now is just we try to do a best effort kind of thing. We hope to get a better support, like debugging message or indication that some optimization has kicked in or some optimization has not kicked in because of something. That we should keep improving the error messages like that.
Is there any particular language feature like closures or something that isn't supported by the code generator at all?
Oh no, we support closures.
Okay, so there are no hard edges. Everything is supported. It's just a question of performance.
Yeah, everything is supported. We have two backends. One is translated to C, which as we imagine, there's got to be some limitations because the memory management and all that are different from Julia. So if you take the C backend, there's a limited set we can support. If we are not able to optimize the function, we'll give an error message that we cannot optimize your function, and with some indication on where it goes wrong. But with the LVM backend, we basically support everything. Thank you.